Hello everybody, I'm back again. Once again, I need some practice doing some physics, so I figured I might as well share with you guys what I'm covering. And right now I'm in my electromagnetism class, or electrodynamics class, reading out of Jackson. In terms of news, I didn't do too great on the first exam I had with this class, and it was over some pretty simple stuff, over electrostatics, and I didn't do as well because I changed my study routine, and making content with the StatMech was kind of a good way for me to do and to study, because it allowed me to explain things to you guys and what I'm doing and what I'm learning. So as a consequence, I've decided to kind of go back to that format and pre-record a bunch of videos. I'm probably going to upload this way down the line. I don't know what date even. But nonetheless, I'm going to be working through a couple problems in Nayfeh, and in particular chapter 7 of Nayfeh, in which we're covering current densities and Ohm's law for current densities. That's what this particular question actually covers. In this particular question, we have our lovely little steady current being applied, or being surrounded by an effectively just an infinite medium that has not only a conductivity of sigma sub c, but also a permittivity of epsilon naught, so basically just free space, just some generic medium, right? And we're applying some current into this particular steady state, right? This steady state can be anything, it's just our amorphous steady state object, right? So we have a few things we want to solve for. Namely, in this example, we want to solve for the current density, we want to solve for the electric field, the potential, and then also the capacitance, right? So in order to do so, we have to apply Gauss's law, like we do in electrostatics. So in the first case, when we're looking for our current density, we know that not only does the current, or the wire applying the current, supply an element of that charge density, but also our Gaussian surface per se that encloses our object of interest, right? So we write our surface integral, or closed path integral of j dot dA, into two pieces, one of them being the wire and one of them being the surface, right? However, and I cannot recall for what reason, I think it could just be Gauss's law for the wire off the top of my head. Let me refer to my notes really quick, just to make sure I'm not saying something that's necessarily correct or incorrect. No, it's just Gauss's law for currents. So we apply Gauss's law for currents, which says that the dot product, or the integral of the dot product of the current density and the area that we encircle is equal to 0. So we break that up, but we still have our sum, right? So that means that the wire, I should write, or the integral of our wire over its current density is equal to the surface integral, or rather the negative of that, because it's equal to 0, obviously. And that's what happens when you move terms around. But we can also set one of these two being equal to our current. And the one we want to set equal to our current is our is the one for our wire, right? So when we do this particular operation, we can say that for our wire, we have j dot dA is equal to the current, I, and we just take the dot product and we apply the integration like we do with standard Gaussian integrals, right? Because you remember from electrostatics, E dot dA for a sphere is similar to E, or the magnitude of E, these are vectors, 4 pi r squared, right? That's how you would evaluate that particular integral. Yeah, once we do that, we can just solve the left-hand side for J, and when we do that, we get that our current density is equal to the magnitude of the current divided by 4 pi r squared. in the r hat direction, obviously, because current density is a vector. Also, I wanted to clarify there's a reason why we're able to do some of these approximations in this formulation, and that is because we are assuming that the current itself is unaffected relatively by electric fields around the current density as well. If so, then we wouldn't have a constant current density, and then we wouldn't be dealing with an ohmic potential, and then not an ohmic potential, what on earth am I saying? An ohmic material, and if we're not using an ohmic material, then we can't apply Ohm's law for the current densities, right? Which is what we do in part B. And in part B, we are looking for the electric field. Well, thankfully, we know that our current density is proportionate to our electric field by an amount of our, by the conductivity. I can never remember conductivity as a word, but yeah. So we just move some terms around and we make that substitution, or actually we just divide our answer in part A by sigma sub c, and we actually get our electric field. That should be in the, oh goodness, in the r hat direction. I meant to write r hat, not r squared, so let me correct that there. Oh my gosh, I'm doing the same thing again. There we go. R hat, my apologies. Sometimes your brain goes and it gets a little bit crazy, but yeah. From there, it's just our standard procedure relating our electric field using the integral of of r, from r to infinity, in order to evaluate what our potential is, V. And when we do that, we get a pretty standard result, except we multiply it by a quantity of I, and then obviously we don't have an epsilon naught in the denominator. We have our our conductivity, sigma c, right? So that's what we do for the potential. We just take that standard integral. And then for the capacitance, we just need to know what the total charge is divided by the potential V. We already know that we can find the potential, or the contribution to an electric potential from a point charge as being phi is equal to Q divided by 4 pi epsilon naught R, right? So naturally, move some terms around, we can get Q in terms of our potential phi, and because we know that we're operating over some distance, we can just substitute phi for V if we wanted to in this case. But nonetheless, we can use these substitutions here, and also assuming that we take our Gaussian integral to be at this radius r, we would change our lowercase r, just being some generic radius, to our actual fixed radius of r, where we set our Gaussian surface, and then we just divide our total charge q by 4 pi epsilon naught big R, and then we just get our 4 pi epsilon naught R as our capacitance. That's kind of a good little introduction to current density, right? So we can apply Gauss's law for current density, assuming that we are neglecting any sort of wacky edge effects or constant or changes with the application of some current. We can then use Ohm's law for current densities to solve what our electric field would be, and then we use our standard relationships with potential and capacitance to find those particular values as well. Yeah, that's that.